Hello, everyone, and thank you for joining us on this episode of the Akkad and Koka Report. I'm Michel Akkad in San Francisco, and I'm joined by Anish Koka in Philadelphia. Today, we are going to take a deep dive into medical epistemology. How do we know that statins work, or that they don't work? How do we know that stents are useful to treat stable coronary disease, or that they are worthless? How do we know that a new cancer treatment saves lives? Billions of healthcare dollars are at stake in the answers to those questions. And for decades, those answers have been adjudicated from within an arcane field of human inquiry that seems to combine the precision of mathematics with the accuracy of astrology. We are talking, of course, about statistics and statistical inference. To help us understand better this mystical science, we have as our guest Michael Acree. Dr. Acree obtained a bachelor's in mathematics from Oberlin College and a PhD in clinical psychology from Clark University. And he has spent his entire career working at the University of California, San Francisco, as a data scientist and a teacher of statistical science, helping countless researchers make sense of the data they had obtained. Michael Acree is now retired from UCSF and is completing a book on the history and philosophy of statistical inference, and he is a great person to tell us the whole truth about what is sometimes referred to as the science of mendacity. Michael, welcome to the show.
Thank you very much. That was a great introduction.
It's great to have you. So I'm going to start by telling you what is the popular belief or conception about how we understand whether a treatment works or not. And the way we think about it is that there's a new treatment, and we know about randomization. We're going to take a group of patients, we're going to apply the treatment to another group, is going to serve as a control. They're going to be randomly assigned to whether they get the placebo or the treatment. And then outcomes will be collected at the end of the study period. And then the data will be given to a statistician to put it into the statistical machinery. And out of that will be, with bated breath, the scientists will wait for what the p-value is on whether the improvement in outcomes is statistically significant or not. And then if the p-value is less than 0.05, they can rush to the media or they can get their grants funded, or they can go to the FDA and get their medication approved, and that sort of thing. Is that a good rendition of what goes on?
It is a good rendition. The only thing I would add is it's remarkable that the procedure you just described is the only one that medical scientists can envision. That's the only accredited procedure we have for answering a question like whether a given treatment works, which is to observe random aggregates of individuals and then compare the respective means.
Right.
For those who did or didn't get the treatment.
But what's wrong with that approach? I mean, we've been doing this for about 50, 60, 70 years. I don't know how long. I mean, for a long period of time.
The approach isn't intrinsically wrong or lacking, but it's funny that we think of that as the only way. If we want to decide the bias of a coin, it wouldn't be wrong to toss it a bunch of times, but it also wouldn't be wrong to inspect the coin to see whether it had a physical imbalance. And now an analog of that activity in medical research would be bench science, for example. Study the properties of statins and how they work, and then we might have an idea how it worked, the kind of person on whom it worked, under what conditions, and there would be less need for thousands of cases selected at random and then to make a decision based on the average.
Right. But the pushback on that approach would be that, our knowledge of biology is always imperfect, and there have been many treatments that were promulgated on the basis of biological plausibility. But then when we run the clinical trials, we find out that, lo and behold, the stuff doesn't work.
Sure. And no method is going to be perfect and will always give us the truth. And we're going to talk about the problems with statistical method today. Generally, if we regard if we think about an intellectual marketplace of ideas, in the long run, the best idea wins, errors get corrected, and so on.
Right. So, I mean, are you saying that this is, what are you saying? I mean, are you saying that these randomized trials and whatnot are I mean, eventually we will know one way or the other whether we run the trial or not? I'm not sure I was following your point here.
The
Sorry
only
about
point I was making is it's remarkable that we take the method that you described, the statistical method, as the only method.
that. Okay. Okay.
There
Right.
are
Right.
other methods.
Right. It may be that 30 years from now, people will look at our era and say, how primitive it was, and we have other ways of gaining knowledge. But let's since it is what we're used to and what we hear about, what we're bathed in. Tell us a little bit about this procedure, because I'm not a scientist, but I know that people talk about problems, theoretical problems, with what we infer when we go through this procedure, when we randomly assign, a treatment to a group, and then collect data down the line, and then compare the means, and then infer something from that difference between the means. What are the theoretical problems with that approach?
Well, one of the problems, and this is a strong talking point by the Bayesians, is that when we do this approach, what we're calculating as the p-value, the ultimate outcome, is the probability of the data given the hypothesis. We set up a null hypothesis, which we usually don't believe for a minute, that there's no difference, the treatment is ineffective. And then on that basis, we calculate the probability of getting results at least as extreme as those we obtained. And if that probability is less than 0.05, then we decide to reject the null hypothesis. One of the things that's weird about that is the triple negative logic. Lancelot Hogben said, for what reason should the laboratory research worker be eager to take advantage of a procedure which can merely assign a low probability to erroneously asserting that the treatment is useless?
A low probability to erroneously asserting that the treatment is useless.
Yes,
this is right. This is what the p-value tells you.
Yeah.
It tells you there's a low likelihood that you would be wrong if you said that the treatment was useless.
Right.
And that's what we used to say, therefore the treatment works, right?
Right.
Okay. It does sound weird when you put it on, in those terms.
But I mentioned that the p-value is also the probability of the data given the hypothesis. There's a strong tendency on the part of practitioners to interpret that as the inverse, as the probability of the hypothesis given the data.
Right.
Many people will say a p-value of 0.05 means that there's a 0.05 probability that the hypothesis is true. But the probability of the data given the hypothesis is by no means the same as the probability of the hypothesis given the data. It's the difference between the probability that someone is a pope given that they're Catholic and probability that someone is Catholic given that he's a pope.
Right. Yeah. That certainly is a very, very important and widely misunderstood, I think, by the population at large, by journalists when they write their pieces, and by most doctors, I would imagine, and maybe even many scientists. Perhaps. So you're right. It's the probability of the data. It's not the probability of, as you said, of the hypothesis being true. It's or false. It's just the probability of the data if the hypothesis were assumed or.
Right. And in the traditional theory, the whole process culminates in a decision, yes or no, respecting a hypothesis. But that practice can be criticized too. A hypothesis isn't something like a piece of pie offered for dessert, thanks or no thanks, yes or no, accept or reject. Um, but that's what the theory
Right.
says. And
Right.
then what our probability is a probability of long run frequency of certain kind of errors in a long series of trials. And
Because the statistics assume that this is a sample from a hypothetical long right repeated such experiments, right? I mean, this. Okay.
right.
But
Okay.
I mean, so this is the error of the transposed conditional is that it's been termed as that, right?
Yes.
Exactly what you're saying in terms of, Catholic, probability of being the Pope if you're Catholic versus the probability of being Catholic if you're the Pope. But so, and the issue is in terms of actually making some type of inference moving forward once you have data, in terms of traveling between those two states, one needs the prior, correct? So it seems like, would it seem like in a frequentist world that you're just pushing the hard work towards the end, meaning if done correctly, you generate your p-value, you generate your data, and then it requires the prior, i.e. the hard work to generate the to try to sort out whether the data supports the hypothesis or not. Whereas in Bayesian thinking, it seems like the work is upfront, where you have to kind of define your prior and then do it. So is it not? Is this not the same? Aren't we really just at a 30,000 foot level? Why is it that different?
That's a very good point. And I hadn't acknowledged the Bayesian perspective yet.
Sorry.
Yeah, so the Bayesians do claim that point in their advantage, that the research decision about whether to accept or reject, for example, ought to depend on a whole lot more than just the sample data at hand. There are many other factors to be taken into account, which they summarize numerically in their prior belief about the hypothesis. And then the result at the end is not the decision about the hypothesis, but a distribution of belief about the hypothesis corresponding to their distribution of belief about the hypothesis before they did the experiment. So
Okay.
they count that as a point in their favor, that they bring in the whole inferential process, whereas the frequentists are looking just at one small piece of it. The argument can go back and forth about how realistic it is to summarize all the prior evidence in one distribution or a number, and so on.
Yeah, let's before I think it's important. I'd like to spend some time talking about the Bayesian analysis. But before we get there, let's just stick with the standard approach here. There was one more point I wanted to talk about. Is this p-value of 0.05? Where does that come from? Why 5% as opposed to 6% or 3%? Is it a tradition? Is it a nice round number? Is it?
I've never seen a good explanation of that, but I think I've finally found one, and it's very interesting. Harold Jeffreys, in his book, The Theory of Probability, in 1939, said that it had been habitually found by astronomers in the 19th century that, backtracking a moment, the prototype for significance testing was the practice of using the normal distribution and probability as a basis for rejecting discordant observations in astronomy. Astronomers would typically make several observations of the time an eclipse or whatever, and they would vary a little bit due to the personal equation or funny things in the atmosphere or whatever. So the practice gradually evolved, and it was a controversial one of striking an average as an estimate of the true value. But sometimes you get a wild one. And the issue was whether to reject that one before striking the average. And there were arguments both ways. And eventually, a statistical criterion was proposed by William Chauvenet in his book on astronomy in 1863. He proposed to calculate the mean and standard deviation of the values that you'd obtained, a dozen or however many, and reject any observations beyond the point where you would expect only half an observation to lie.
Mm-hmm.
Does that make sense so far?
Reject an observation beyond the point where you would expect only half an observation to lie.
Right. So we can get our calculate, assuming a normal distribution for these observations, calculate mean and standard deviation, and we can multiply that by our total n, and we can then see the point beyond which we would expect half an observation to lie. And if there are any observations out there, reject them, recalculate the mean and standard deviation, and keep doing that until you don't reject any more observations.
Okay.
That was a simple, straightforward procedure, and it caught on really quickly. And Jeffreys observed, or says that it had become a rule of thumb that any observations beyond about 2 standard deviations were good candidates for rejection. So that was just kind of a rough rule of thumb among astronomers. Okay. I think that 2 standard deviation rule came about because if we have a sample of 10 observations, then the point beyond which we would expect half an observation to fall is about 2 standard deviations from the mean, because half an observation would be 5% of the sample. It would cut off the outer 5% of the distribution.
Okay.
Okay. Yeah. So I think that was the source of the original 0.05 level, but it wasn't something that became institutionalized for a while. And that came about because in 1925, R.A. Fisher published his book, Statistical Methods for Research Workers, and he appealed to Carl Pearson for permission to reprint his statistical tables. Pearson's biometric laboratory had spent years compiling tables of various statistical distributions, and that was an enormous labor in those days with hand calculators. Student, the inventor of the t-test, said that the calculator in his lab had been bartered from Noah on his original voyage, but he hadn't been able to keep it dry, and his assistant Summerfield in the lab wasn't strong enough to turn the handle. So anyway, Pearson or Fisher appealed to Pearson for permission to reprint his tables. The practice in statistics book up to that time was to print values across the whole distribution. Pearson refused Fisher. He'd given permission to other authors. There's reasons to suspect that personal motives were involved. Pearson was a very vain man, and he and his team had been working for years to develop the distribution of the correlation coefficient in the sample, and periodically they would publish updates of their work in their journal Biometrica. And Fisher read one of these progress reports in 1915 when he was 25 and sent in a complete solution within a week. So reason to believe Pearson's pride may have been injured there. He published the paper. That's one of 2 occasions, it said, when they were known to agree on anything. The second thing that happened was a little bit later on. Fisher determined, in 1922, I think, that Pearson, who had invented the chi-square test, made a mistake in the degrees of freedom, because when it was the chi-square test was applied to a contingency table, degrees of freedom ought to be the number of rows minus 1 times the number of columns minus 1. And Pearson was using the number of cells minus 1. And Pearson never agreed that he had made a mistake there until his death in 1937. So there were these two kind of personal insults that were going on that we can expect as a reason for his refusing Fisher's permission to reprint the statistical tables. So Fisher got around copyright infringement by reproducing just the 0.05 and 0.01 levels in the tables. That's the only values that were published from the normal or the t-distribution.
In his textbooks, in Fisher's textbook.
Right, in Fisher's book.
Okay.
And after Fisher, the subsequent generations of textbooks, Snedeker and so on, all copied him in reproducing just the 0.05 and 0.01 levels. Nobody bothered to represent the whole distribution except for the normal distribution in most cases.
And the tradition of using the 0.05 level dates from around that period of time, as far as you can tell?
Right. It was after Fisher's textbook in 1925. That was really the institutionalization of that level.
Okay.
And after that practice was adopted by other textbook authors, then the 0.05 and 0.01 levels were all that investigators ever saw.
Okay. And so then the 0.05 becomes sort of a not only a rule of thumb, and then as things develop in modern medicine and drugs have to be approved by using certain criteria, or papers have to be published, or grants have to be funded, then it becomes a convenient sort of level to go by to make decisions around, right?
Right.
I mean, that would be the idea.
Yeah, the institutionalization of the 0.05 level essentially meant that now with significance testing, we had an automatic impersonal criterion of knowledge.
Right,
True or false, P less than 0.05, yeah. So it was irresistible, it was philosophical heroin.
Okay. And of course, we all have heard of the practice of p-hacking, of trying to adjust your data somehow in order to meet that level, right? To come. Have you ever been asked to p-hack, or are you complicit? You're retired now, so maybe you can you can tell us. Did researchers ever come to you and say, "Listen, it's 0.06. Can we do something about it? Can we throw out this data or that data?" Or
nobody has quite phrased it in terms of p-hacking, that I want you to get this to 0.05.
Right.
But essentially, that was done many, many times by certain investigators, but not all of them.
Mm-hmm.
So it was routine for me to be asked to run a huge matrix of thousands of correlations, let's say. And it takes the investigator 5 minutes to run through and check and see that none of them are significant. What's going on is well below chance. So they say, well, let's try a log transformation. Or let's split the sample, and you just keep getting more requests until they get what they want. That's the way it works. And sometimes I complained about that.
Right. But that's the way the world turns. I would imagine.
That's right. They need grants for tenure, publication. Their lives depend on the P05. So.
Right.
Yeah.
It's remarkable, but then to go back about what we were saying earlier about this, that what the p-value means. Again, it's not the probability of the hypothesis being true. It's only the probability of the data given the hypothesis, right? And so, so as Anish was saying, there's one has to make yet another leap to conclude something about the hypothesis itself.
Right.
Okay,
right.
And that's where what Anish was saying, the Bayesian come in. When did that come about historically? When did that?
One
Go
question
ahead.
before you get to the Bayesian, now that we're talking so much about p-values, is what do you think that p-values and frequentism may be rescued by confidence intervals?
Um,
Do you have a tongue twisting explanation for a confidence interval that Michelle can slowly repeat?
um,
What does it mean?
Confidence intervals have been the most commonly advocated solution to the problem of p-values, but I think it's a very limited solution um, because it only solves some of the problems. Uh, Confidence intervals avoid the weaknesses associated with the decision aspect of the procedure. So a confidence interval gives us an estimate in place of a decision. That's an advantage. Otherwise, the same statistical apparatus is in place. The reason confidence intervals never caught on in psychological research, I think, is that psychology has tended to take small samples, 30, 50, 100 subjects, and confidence intervals based on those sample sizes are wide enough to drive a truck through. So they're pretty embarrassingly useless. In medical research, it's a little different. They typically involve thousands of cases and can get a serviceably narrow estimate.
Okay. So the Bayesian. So now we see that frequentism, there are these problems, this aspect of decision making, that really seems inappropriate, right? So what do the Bayesian, when do they come on the scene, and what do they say? Anish was summarizing or alluding to them. They say that you have to articulate what your prior expectation is, or what your prior belief is, right, and factor that in.
Right. The Bayesians depart from the frequentists fundamentally on their definition of probability. The modern concept of probability is dualistic in that it adverts on the one hand to a relative frequency conception, and on the other to degrees of belief or evidence, and so on. That was built into the concept from the beginning, really by Bernoulli. And the first attempt to really define probability in a systematic way, I think, was made by John Maynard Keynes in his dissertation in 1905. That was published in 1921. And he argued that probability was fundamentally a degree of belief, which in certain cases, like games of chance, could be expressed as a relative frequency probability. And that was the view taken later by Harold Jeffreys that I alluded to. And later in the 20th century, the prevailing view became the positivist empiricist view that, no, that's not true. That sounds subjective and vague and all of that. And the scientific concept of probability has to be a relative frequency probability. So that was a prevailing view through the 20th century, that probability means a relative frequency. Problem with defining it that way is that it's hard to make it relevant then to decisions and beliefs and those kinds of things.
Right, right.
That was really what led Neyman to design his theory, which is the received theory now of statistical inference, as a decision theory, because he insisted that probability didn't have anything to do with inference or belief or knowledge. It was just a decision theory, and the probability was about the relative frequency of errors of different kinds.
So I'm interested in this. This question about this degree of belief, because now it seems to have been we hear about it, at least in our circles, frequently. People say, we're Bayesians now, and so forth. So, when did that emerge? How long ago? Or, recently, or the last 20 years? Recently.
Yeah, in 1963, I gave that background a moment ago to say that people were thinking systematically about probabilities, degrees of belief from the beginning of the 20th century. But this was more abstract mathematical development, not affecting scientific practice until the latter half of the 20th century. In 1963, there was a Psychological Review article which introduced Bayesian statistics to psychologists. And that was kind of a propitious time because cognitive psychology was just born about 1970, and Bayesian theory appeared to be the only way of quantifying reasoning or thinking in cases of uncertain inference. And so it was an instant model of human reasoning. It was assumed to account for all human reasoning. That helped to popularize it in that field. Bayesian statistics never caught on as a way of analyzing data, even by Bayesian statisticians or cognitive psychologists. But it was believed to be the way the human mind works.
Yeah, so that's where I have some trouble because it seems to imply that when we go about our business, our day-to-day business, we make decisions based on some kind of computational thing. I think that there's a 62% chance of this, and therefore I do that, or that, which sounds a little suspect to me, or seems a little suspect to me.
Yeah.
So is there any evidence that we think, we had a guest on our podcast a few weeks ago, Gary Klein, and we didn't delve into this topic, but he mentioned it offhand. He said, that's not how, he's a cognitive psychologist, and he's sort of outside of the mainstream, so he doesn't view things that way, right? He doesn't view that the mind is sort of a constantly computing things. Is there any evidence that the mind works that way, as a computational sort of machine that's always weighing probabilities and priors and that sort of thing?
Well, of course, the people in the field, the advocates would say we have 50 years of evidence about that, but I think it's not quite that simple. Most of the evidence there was a lot of research done in the 1970s and 80s to see whether people reasoned according to Bayes' theorem, and it generally showed that they did not.
Okay.
Yeah.
But is this not something that we do intuitively as clinicians in terms of when we're presented data, whether we're presented it in the form of a paper or presented in the form of a patient in front of us? Aren't we intuitively, aren't we all intuitively Bayesian? Meaning, it almost seems like frequentism is a effort to unlearn what we do naturally, because apparently what we do naturally is subject to all these biases that, So is Bayesian thinking simply unlocking what we do, naturally? So, Michel, what is your problem with that, Michel?
Yeah, I think I don't think. I think in Bayesian theory, there's a quantification aspect to how you make the decisions that I don't think is there. When you judge the value of a patient, when you say, well, I think this patient has X, you're not saying my diagnostic impression is that the chance is 62% that the patient has, is in heart failure, and 33% that they have pneumonia, and 12% that they have this. You don't. So this computational aspect is not there. You apply a judgment. I think this is what Gary Klein was telling us on the previous episode. You just make a judgment, and Michael, is that correct, or am I?
Yes, I would agree with you so far. In response to what Anish was asking, that Bayesian is just a formalization of our intuitions. One reason I would question that is that Bayesian problems are hard. If you give psychologists who supposedly know Bayesian statistics a Bayesian problem, they can't do it in their heads. They can't even do it if you give them pencil and paper. But yet somehow the nervous system is supposed to be able to have Bayes' theorem hardwired in. Yeah.
So your beef is with attempting to quantify these probabilities. Perhaps.
That and more, I would say. The fact is that Bayes' theorem is a way of combining evidence. And it's the only formal way of combining evidence that's widely known. So from the beginning, it's been assumed that that was the only way and that it was universally applicable. The conditions under which it's valid are not very widely appreciated. I'd like to talk briefly about 2 or 3 problems, limitations of Bayesian theory. The one I make the most of in my book is that Bayesian probabilities force probabilities to behave like chances. They force us into two-sided bets or into committing all of our chips. Let me see if I can give an example. Let's say I have no idea at all who will win the election presidential election in 2020, but I think Larry Sharpe has a 5% chance. That's not necessarily realistic. I wouldn't defend it, but it's an intelligible set of beliefs. Bayesians don't have any way of handling that situation. They can only handle it by putting 5% on Larry Sharpe and distributing the remaining 95% evenly across all the alternatives. The alternatives in this case aren't even well defined. We've got write-in candidates, minority parties, and so on. And if you distribute the probability evenly among those, that's not the same thing as having no idea. That makes it's a much stronger claim to say the probabilities are all identical across those alternatives. This is one expression of the fact that Bayesianism has no good way of expressing ignorance, because the only way it can express ignorance is halfway between the certainty that X is false and the certainty that X is true. In other words, 1/2 is a probability halfway between 0 and 1. So that creates all sorts of problems and paradoxes in Bayesian theory. Another problem with Bayesian theory is it has no way of accounting for non-monotonic reasoning. That's particularly a problem in a new area of research, let's say, an exploratory data analysis. You get a new data set and it may prompt you to consider alternatives that you previously thought were impossible or irrelevant. That's not an unrealistic scenario in science or in real life, but Bayes has no way to handle it. The prior information in Bayes theory has to be given with certainty, and we always just build on our previous certainties. There's,
right.
As Sen put it in that article you recently sent, there's no such thing in Bayesian theory as back to the drawing board.
Right, you have to, right, you build on your priors and you keep building.
Right. The third thing I would mention differs from the first 2 problems in that it's potentially remedial, but it's not often remediated. And that is that Bayes always assumes randomness, which when human actors are involved often isn't a realistic assumption. The most famous case of that is the Monty Hall problem. Maybe I should describe that briefly for your readers. a contestant is shown 3 doors and told that behind one of them is a car and behind the other 2 is a goat. And
Right.
she chooses a door, and then the host opens the door and shows her a goat, and then asks her if she wants to change her choice. This problem was made famous about 20 years ago by Marilyn Vosavant, and she argued that the contestant should switch her choice. And she was roasted by mathematics professors all over the country, saying that's ridiculous. Well, she was right. The math professors were applying Bayes' formula, which holds only if the host chose a door at random to open. But people who know the context of the show know that that would be silly. Half the time, or a third of the time, he would be revealing a car, and that would blow the game. He's intentionally opening a door to show her a goat. But 2/3 of the time, when he does that, he doesn't have any choice of which door to open.
Right.
So there's actually information in that choice, opening a door and showing you a goat, and that does change the probability. So it is to her advantage to switch her vote. That's just an illustration of this problem of assuming randomness when it doesn't
Sure.
apply.
So I mean, bottom line is that it's not all that straightforward that Bayesian theory solves the problems that we started off with of making inferences from data.
Right.
Right. Objectively, right? I mean, in some kind of formal, objective way that we can all agree on, right? That different people looking at the same data would just, have to believe X,
Right.
because that's what the data shows, right? So Bayesianism. So Bayesianism, I mean, they would say, well, of course, no. You at that point, each one of us, with Bayesian, each one of us, we're going to have our own interpretation or our own belief by examining the data, because we put our own priors and so forth. And
That's right. And
but if that's the case, then the entire scientific enterprise falls apart. I would imagine. No.
Well, I don't know that it falls apart, but it does raise a question about what Anish was saying about the value of Bayesian statistics. Each of us will have our own individual prior beliefs about the situation, and thus a different distribution of belief posteriorly. But there's a question, I think, about the value of adding that into the procedure formally. If we're all going to have our own priors and posteriors, maybe we should just stick with the published results of the Frequentist test results, and then we can all apply our own priors and get our own posteriors. That's relevant to this paper that you circulated about the what was it, IMCO or something, the trial, the original paper.
The ECMO,
there.
right. I'll put those papers. That's the ECMO paper. That was a recent paper in JAMA. The title of which was should we embrace our inner Bayesian?
Right. They were commenting on an earlier article by Gulliger, I think, the original ECMO trial or whatever it was. And they did a Bayesian analysis, and I think it was an exemplary Bayesian analysis, and they tested a whole range of priors with large variances and small variances and all to see how much difference it made. So if you're going to do Bayesian statistics, I thought that was as good as you could do. But there's a question of how much value is added there versus just presenting the Frequentist results and let everybody calculate their own posterior.
Yeah, I mean, how is the FDA going to approve a drug with that approach?
Pharmaceutical companies have been petitioning the FDA for years to approve Bayesian statistics, and they've so far resisted.
Yes, with bureaucratic wisdom, I would imagine. I have a question. So before we wrap up, I have a question. Both, I mean, all of this work is predicated on using these distribution curves. I mean, and let's take the normal distribution curve, right? So the normal distribution curve. So let's imagine that we can imagine that blood cholesterol is normally distributed. It may be log normally distributed, but let's, for simplicity, say that it's normally distributed. Height is normally distributed, right? Weight is normally distributed. All that stuff is normally distributed, and we use that. That idea is baked into all these analyses, all these whether it's Bayesian or Frequentist or whatnot.
Right.
But the normal distribution is a bell-shaped curve that is open-ended to infinity on either side.
Yes.
Right, which means that theoretically, a man who's 16 foot tall is just part of the bell-shaped curve. It's a rare event, and it should be considered, as completely, part of normality, which is not the case. It's clearly not the case. I mean, in reality, those bell-shaped curves cross the x-axis, or they stop somewhere, or they may not even cross in any place. So they don't cross in any place mathematically. We can say that, the normal height stops at 7 foot and 3 inches, 0.5, or whoever. I don't know who the tallest man in recorded history is, but there's no precision to those boundaries.
Right.
But at the same time, it doesn't go to infinity on either side.
Right.
So what do statisticians think about that, or how is that taken into account by statisticians or the theorists?
Well, this was a lively controversy in the early 19th century when the normal curve was coming into use for this sort of thing. The normal curve was derived originally in astronomy as an approximation to the binomial. And the rationale given then was that any given astronomical observation could be thought of as a sum of a whole bunch of individual astronomical errors. There might be errors in the astronomer's reaction times, or irregularities in the telescope, or this and that, and they add them all up and averages out to the true value. But it was observed, even in those days, as you say, that the normal curve goes to infinity in both directions, and so it was inherently unrealistic. Daniel Bernoulli proposed a semi-elliptical distribution, which he thought made more sense. That's precisely bounded at one end or the other, and somebody proposed a double triangular distribution. The normal curve won out for reasons mostly of mathematical convenience.
Right, because it
was applied to social statistics by the astronomer Quetelet in the 1830s and 40s. That's just when governments began keeping records, keeping large numbers of statistics, and he had access to a file of chest measurements of Scottish soldiers, or heights of French conscripts, that sort of thing, when they're measuring for uniforms, maybe have 100,000 heights, and he was very impressed to see that it formed a normal distribution, just like he was familiar in astronomy. And he inferred from this that the same process was going on, that nature has a true value that she is striving to achieve. And these individual deviations represent errors, essentially failures of quality control at the very highest level. And that's where we get variation in human height or whatever. There were other problems too. If height is normally distributed, then weight, which is proportional to height cubed, can't possibly be normally distributed. So there was a great controversy about that for most of the 19th century.
Right. But my point is that so if we agree that the model is unrealistic, right? I mean, the bell-shaped curve is unrealistic. It's a model.
Right.
How can we expect a non-realistic model to inform our judgment with any certainty. Right. I mean, it can help us, but at the end of the day, we're going to make a judgment.
Basically, I think what was done was simulation studies. We can look at the departures from normality and practice and see how much difference the distortion makes in the final test statistic. And the general report was that non-normality doesn't make too much of a difference under some common conditions. And so people felt free to disregard it.
Yeah, and I'm not saying that that it's not helpful. I mean, you know, the contour. I mean, if you take a population, the normal curve may be very helpful for certain purposes to describe this population. If we're going to describe the population mathematically, maybe the bell-shaped curve is the most important one. But at the same time, we know that human beings are not going to be sort of normally distributed, really, right? They're not.
Right.
And so that tells us about, you know, that points in my mind to a limit, to the limit of using statistics precisely for inference, for you know, for making judgments. It means that we're able to make judgments in other ways, right? I mean that because somehow if I see a man who's 16 foot tall, or you know, I'm going to recognize that man as abnormal, and at that point, so I'm not sure what I'm trying to say.
Well, but Michel, the problem,
yeah.
But the issue is that, you know, you brought this up before in terms of the ability to differentiate what's abnormal from normal without being empiric about it. The 8-foot rabbit,
right.
8-foot tall man.
Yeah.
But the problem is a lot of decisions are made outside of those extremes, and there's a desire and hunger. The part of the reason this is coming up is this is not actually some top-down thing in terms of frequentism or Bayesian modes of analysis. It's not coming from the top in terms of being forced down on the little people. There's actually a hunger amongst folks like, well, not you, but folks like me, for some mechanism to deal with the biases that we have when we make judgments. You know, we all have judgments that we're making, and there's some unconscious bias within these judgments, and so there's some conscious bias. And the niggling question whenever I'm making some decision always is that am I making the right decision? And the same applies to when I'm trying to interpret research. When I'm interpreting research, you know, my summed experiences is why I arrive at a certain judgment. Wouldn't it be great? Wouldn't it be awesome to have some type of truth machine that kind of tells me and is a check on me to kind of check my biases? So the question is how, you know, what is there is there a path forward? There are obviously limitations of Bayesian thinking. There's limitations of frequentism, p-values, confidence intervals. But then if that's the case, what is the path forward?
Well, that's a very eloquent statement. People have been looking, at least since the time of Leibniz, for that kind of automatic guarantee of knowledge. Right. I agree that people have a hunger for it. It's coming from the bottom up. I don't think that there is such a thing, and we should be very, very wary of it if anyone proposed it. Yeah.
But that's essentially what people, I mean, what we seem to think that we have. I mean, you know, notwithstanding the criticism that statistical inference is under right now, but for the most part, I mean, that's how, you know, bureaucracies work on the assumption that the statistical machinery is a truth machine.
Yes.
I think it comes from especially in the medical world, it comes from a desire for not allowing error to happen.
I think it's an abdication of responsibility. Because
No.
when you make a judgment, you're responsible for it, and you may be wrong, and so we're trying to deflect that responsibility onto the mathematical process, right? To say it's not me, it's the statistics.
Well,
No, we have to make judgments, right? I mean, if you have data, you have to decide, do I believe it or not, and then go with it, and then live or die by your judgment.
But I don't think we as a society are ready to turn over decision making to Michel
judgment, to human judgment.
Human judgment, yeah. Well, I think there's a great discomfort with that, because the beauty, and this is mildly. I guess a good thing to relate is evolution. You have massive progress. Well, you have progress that's happened with evolution, but the progress with evolution is largely a result of dead ends. And the issue is that nobody wants dead ends in this world that we're living in right now. So you can argue that the mistakes that we make, and this is true in the history of medicine, is that we have been driven forward by the mistakes we've made and those dead ends. But it's almost seen as uncivilized to do that. And so I don't know what the right answer is, because of course we want to improve. We don't want to improve how we move forward, and we'd like to move forward without dead ends, because dead ends in medicine, in terms of what we're doing, means patients harmed, or patients grievously, or patients dead. So.
Yeah, but I mean, I'm not sure that we've avoided the dead ends because of the statistical inference apparatus.
Well, I don't think. I think it's likely.
People have been,
Michel, it's likely that we're safer because of it.
I don't know. I think.
But I think to go back to the construct of type 1 and type 2 error, meaning I think we are making. The path we're on means that we make far fewer errors, but it may be that what we've given up is what we can't see, and what we've given up is we're progressing forward in a much slower path, or we're not. So there are innovations that are happening the innovations that will never happen that we don't know about.
Yeah, you really can't tell. You really can't tell. It's a very fundamental philosophical question and you can't use history to be able to determine one way or another whether we're better off because of statistical inference or not better off. But it seems to me that we're making judgment, and even in statistical, I mean, now even with the tools of statistical analysis, we are still making judgment, and there are some bad judgments being made and good judgments. And the fact that we can recognize good judgments from bad judgments, the fact that we can recognize progress, that itself is a judgment, right? I mean, progress is a judgment. There's no statistical, analysis that will tell you that you're progressing. Statistical analysis will tell you that you're moving, perhaps, or in one direction versus another, but it won't tell you what direction is better than the other. So just the idea of progress itself has to rely on judgment. And so I say we can. I suspect we can do away with it and be completely fine. I suspect the great benefit of clinical research is the shared experience, and you could do a lot of clinical research without the statistical analysis. You can have randomized control trials, which there's value in having this parallel treatment of patients, and we're making judgments out of that experiment, even if we don't apply the analysis. Right? Because then if the treatment effect is minute, it's going to be minute, and the statistics are not going to help us, right? So one way or another, if they're minute, we're gonna be suspicious of the statistical analysis, and if the treatment effect is obvious or the safety is obvious or whatnot, we actually don't need the statistical analysis, right? We either don't need it or it's not helpful.
I'm very much impressed with the eloquence of Anisha's concern and question here.
Yeah, what about mine? What about
and I'm very much impressed with your answer. You said exactly what I would have wanted to say.
Oh, okay, good.
Especially about personal responsibility. Anish is right that we don't want everything left to Michel Acad's judgment, but it isn't. We have thousands of Michel Acad's. We all have our own judgments and decisions. Michael Polanyi speaks of the need to stake our shirts on our work um, and be responsible for it, to make a commitment. And that's something that we shouldn't put off onto a formula. We should be wary of a formula which told us what to think, whether we agree to it or not. I appeal again to the idea of the marketplace of ideas versus a top-down structure that tells us what to do.
Right. And the marketplace means what's that?
But and I forget who has written this. I love reading a lot of the statisticians, because some of the great statisticians today are like philosophers. So Stephenson and Frank Harrell, and I'm looking forward to your book as well. And I think Deborah Mayo. These are all, they're wonderful writers. And I think one of the things that Stephenson, I believe, has said when he talks about Fisher, in terms of what you're talking about in terms of ideas and allowing the best ideas to bubble to the top and some ideas die, is that Fisher's hope was that his mechanism was a way of applying evolutionary pressure to ideas. Right? So if the idea was good enough, it should survive Fisher. If it's not good enough to survive Fisher, then which is a fair thing, But of course, the problem is, we ran into this whole population health buzzsaw, and all of population health and primary care.
This is where we get fooled, because Fisher historically, he came at the right time to serve the nanny state and the welfare, and the bureaucratic state, the bureaucratic apparatus. So in a way, Fisher's idea is surviving right now, not necessarily, because it's necessarily a good idea, but because historically it serves a good purpose, right? It doesn't bring us closer to the truth, but it has a pragmatic utility here.
Yeah. Right. I guess I'm.
I have.
Yeah. Right. No, that's okay. My concern, is that my big concern with all of this is that we don't know of the innovations that we don't have, because we have folks in the FDA and wherever in kind of straitjackets. And what I get upset with as a clinician is that I feel like things are backwards. I mean, I feel like the statisticians frequently will say, when some statistician has a cold and he goes to a doctor and the doctor says, "Oh, take Sudafed," and the statistician then will look up all the evidence for Sudafed, and he says, "The doctor just told me something which has zero evidence, no evidence at all." And it's.
But let me say something here that you can. I think there's a very helpful work of the statistician or somebody who's in tune with the biases to point those out. But that's distinct from the actual inferential analysis. Am I correct here? That I think, somebody can point out in the bias of your in the design of your study or in your reasoning where you might be biased, where there might be confounders, and randomization is helpful to take care of confounders and that sort of thing. All of that is very good. I'm not poo-pooing that. But at the same time, once you have data and you need to make a decision about whether the data means something, that ends up being ultimately a matter of judgment, and the numbers won't help you.
Yeah.
Okay. Shall we stop here?
Yes.
Anything else to add, Mike?
Good last.
No, I'm tremendously impressed with the ground that we covered and with the spirited exchange.
Well, that's great. Well, that's thanks to you. Thanks to you, because you really so you sort of provide with very very clearly the info to cover that ground. So
and then Nish provided the challenge. So yeah.
Right. So we look forward to hearing from you and the progress of your book. And I don't think you have any kind of social media presence, do you, that we can tell the audience about? Or
no, I don't.
So on the show notes, I will have some of the papers that we very briefly sort of mentioned in passing, but there will be papers that do address the questions we've been discussing. Again, thank you very much, Mike.
Thank both of you so much.
Alrighty. Take care.